Here is a scenario that happens more often than anyone admits. A senior engineer, 5 years of experience, shipped real products, walks into a big tech system design interview. The question, design a RAG-based customer support system. They nail the opening, confidently draws the vector database, the embedding pipeline, the LLM call. The interviewer nods. Then comes the follow-up. Your retrieval latency just spiked to 8 seconds under 500 users. Walk me through exactly why that happens and how you fix it. The candidate freezes. Not because they don't know RAG, they've built one, but because they only know the happy path diagram, not the failure modes that production actually throws at you. That freeze costs them the offer. And here is the brutal truth. This is not a knowledge gap. It is a mental model gap. By the end of this lecture, you will have the exact 7-pattern framework that closes that gap permanently. So what exactly do you need to master to never freeze in that room? Let me show you the complete map. In 2025 and 2026 big tech high hiring cycles, and yes, this includes its Naver, Kakao line, as well as Google, Meta, and Amazon system design question cluster around 7 core patterns. Pattern 1, LLM serving architecture, covering inference optimization and batching strategies. Pattern 2, RAG pipeline design, where retrieval latency and index freshness are the kill zones. Pattern 3, agent orchestration, because multi-step tool calling systems break ways that single LLM calls never do. Pattern 4, vector database selection and scaling. Pattern 5, streaming response architecture. Pattern 6, cost-optimized model routing. And Pattern 7, observability and evaluation pipelines, the one most candidates completely skip. Here is what is interesting. You do not memorize 7 independently. They share 3 common evaluation axes that interviewers use as their scoring rubric. We will name those axes in the next section, and once you see them, every AI architecture question becomes a structured exercise, not a guessing game. Let me give you the historical context, because understanding why this shift happened makes you a better candidate in the room. Before 2022, system design interviews at Korean big tech, Naver, Kakao, Line, focused almost exclusively on distributed databases, message queues, and API gateway patterns. Standard byte go territory. Then GP 3.5 dropped into production in early 2023, and everything changed faster than hiring teams could update their rubrics. By Q3 2023, Naver's Hyperclova X team was running inference at a scale that required custom KV cache management. Kakao was integrating LLM calls into KakaoTalk flows where a 3-second timeout was a user experience catastrophe. Line's ML platform team was designing multi-region RAG systems for Japanese and Taiwanese markets simultaneously. By 2024, internal interview guides at these companies had rewritten to include mandatory AI infrastructure questions at the senior level. And by 2025, if you cannot speak to LLM serving trade-offs in an engineer loop, you are screened out before the architectural deep dive even begins. This is not a trend, it is the new baseline. And most candidates are still studying the 2020-21 playbook. That is the real gap. Now here is the framework that ties everything together. And this is what separates candidates who get offers from candidates who get polite rejection emails. Every AI architecture question, regardless of how it is phrased, is being evaluated on exactly 3 quality attributes. First, availability. Can this system serve requests when a model endpoint goes down, when a vector index is being rebuilt, or when a downstream LLM provider has an outage? Second, scalability. How does this architecture behave when concurrent users go from 100 to 100,000? Does retrieval latency stay flat, or does it explode like our 8-second example? Third, cost efficiency. Because a system that works at 10 requests per second, but costs $300 per million tokens, will get killed in the next budget cycle, regardless of how elegant the architecture is. Every slide in this lecture, every pattern we discuss, will be anchored to these 3 axes. When you sit in that interview room and the interviewer asks a follow-up you did not anticipate, you now have a structured lens. Ask yourself which of these 3 quality attributes is under threat, and answer through that lens. That is the framework. Let us now go build the first pattern, LLM serving architecture, starting with the most misunderstood component in the entire stack, the inference server. Last chapter we saw how interviewers spot the candidates who've never operated LLMs in production. Now let's fix that, starting with the pattern that separates junior thinking from senior thinking, the LLM gateway. Here's the junior move. Your application calls OpenAI directly. One API key hard-coded somewhere, no rate limiting, no fallback. Works fine in a demo. Then you hit 10,000 concurrent users at Kakao scale, and your entire service goes down because OpenAI returned a 429. The LLM gateway is a centralized proxy layer that sits between every client and every LLM provider. It owns 4 critical jobs: authentication and API key rotation, rate limiting per tenant or per user, model version routing, so you can A/B test GPT-4 versus Claude 3.4 without touching application code, and cost metering, so your finance team doesn't cry at the end of the month. Think of it as the API gateway pattern you already know, but with LLM-specific intelligence baked in. Tools like Light LLM, Kong AI Gateway, and Porky all implement this pattern. But here's what most candidates miss. The gateway is not just an ops convenience. It is a hard architectural requirement the moment you serve more than one model or more than one team. And the reason why will surprise you in the next scene. Alright, let's walk through the actual request flow, because this is exactly what you'll be asked to diagram on a whiteboard. A request comes in from your client app. First stop, the gateway's auth middleware validates the JWT and resolves the tenant identity. Then the rate limiter checks, is this tenant within their token per minute budget? If yes, the request moves to the model router. This is where it gets interesting. The router checks your routing rules. Is the request tagged as high priority? Route to GPT-4. Is it a bulk summarization job? Route to a cheaper model. Now, what if primary model endpoint returns a 503? This is where the circuit breaker fires. The gateway does not retry blindly. That's a classic mistake that turns a 5-second outage into a 60-second cascade. Instead, the circuit breaker opens and the fallback routing rule kicks in. Maybe you back to Claude, maybe you fall back to your own self-hosted Llama deployment. Naver's Hyperclova X infrastructure uses exactly this kind of multi-tier fallback, primary cloud LLM, secondary self-hosted, tertiary degraded response. The response comes back, the gateway logs token usage to your cost store, and the client gets its answer. The entire flow adds roughly 5 to 15 milliseconds of overhead. But wait, what happens if the gateway itself goes down? Here's the uncomfortable truth that most architecture guides skip. The gateway itself can become your single point of failure. You've solved the LLM reliability problem and created a new one. In interviews, this is the trap. Candidates who design a gateway forget to make the gateway highly available, get marked down immediately. Let's compare the two extremes. Direct LLM calls, zero added latency, zero operational complexity, but no unified rate limiting, no cost visibility, and when you want to swap models, you're touching every service. Gateway pattern, 5 to 15 milliseconds overhead, one more component to operate, but you get centralized control, fallback logic, and cost metering. The latency cost is real but almost always acceptable. Your LLM call itself is 5 milliseconds to 3 seconds. Adding 10 milliseconds to that is noise. Now, how do you make the gateway HA? You run it stateless, behind a standard bouncer. 2 or 3 instances across availability zones. Rate limit state lives in Redis, not in process. That's critical. If your rate limiter state is in process, you lose it on restart, and your tenants get free quota resets. At Cacao scale, they run dedicated gateway clusters per region with Redis cluster as the shared state store. The rule is, the gateway must be horizontally scalable and stateless. Any state, rate limit counters, circuit breaker state, cost accumulators, goes to an external store. This is the pattern. Now let's go deeper into what happens inside the LLM inference layer itself, because that's where the real cost explosion lives. Let me give you a number that should scare you. A naive LLM serving setup, one request at a time, no batching, no memory optimization, utilizes roughly 20 to 30% of your GPU capacity. You're paying for an A100 and using it like a 2019 MacBook. In interviews for companies like Naver or Cacao, if you can't explain how to fix this, you will not pass the AI infrastructure round. There are 3 optimization techniques you must know cold. First, KV cache reuse. Every transformer layer computes key and value matrices for every token. If the prefix of your prompt is the same across requests, think system prompts, few shot examples. You can cache and reuse those KV tensors instead of recomputing them. At scale, this alone cuts prefill latency by 40 to 60% for prompt-heavy workloads. Second, continuous batching. Naive serving waits for a full batch before processing. Continuous batching, also called in-flight batching, inserts new requests into an ongoing generation step the moment a slot frees up. This is the single biggest throughput win for variable length workloads. Third, quantization. INT8 or INT4 waits cut GPU memory by 2-4x, letting you fit larger models or more parallel requests per GPU. The GPU cost explosion at scale is almost always a failure to apply these 3 techniques. But knowing the concept is not enough. You need to know the implementation, and that means understanding VLLM. Now let's get into the mechanism that makes VLLM dramatically more efficient than anything before it, paged attention. Here's the problem it solves. In traditional serving, when a request comes in, you have to pre-allocate a contiguous block of GPU memory for its maximum possible KV cache size. If your model supports 4096 tokens and your actual request uses 200 tokens, you've wasted 95% of that allocation. Multiply this by hundreds of concurrent requests, and your GPU memory is full of holes. Fragmented, unusable. This is called memory fragmentation, and it's why naive serving tops out maybe 10 to 20 concurrent sequences on an A100. Paged attention borrows the virtual memory paging concept from operating systems. KV cache is divided into fixed-size pages, say 16 tokens per page. Each request gets a page table mapping logical page indices to physical GPU memory blocks. Pages are allocated on demand, not upfront. When a sequence finishes, its pages are immediately freed and reused by the next request. The result: near zero memory waste, to 4 times more concurrent sequences per GPU, and throughput improvements of 10 to 20x over Hugging Face's naive generate. Call in high concurrency scenarios. At Line's AI infrastructure, they operate across Japan, Taiwan, Thailand. They reported roughly 15 gangs throughput improvement naive serving to VLLM for their translation and summarization workloads. This is not a marginal optimization. It is table stakes. But higher throughput introduces a new tension. What about latency? The trade-off is real, and we'll quantify it right now. Now let's talk about the question every engineering manager and interviewer actually cares. How much does this cost, and when do I scale out? I've seen so many architecture proposals that say we'll use a GPU cluster with zero-cost modeling behind it. That's a red flag. Here's a real cost-throughput comparison across 3 scale points that you should internalize. At 10,000 daily requests, roughly a departmental internal, a single A10G GPU running VLLM with INT8 quantization handles it comfortably at around $0.8 per hour. Total monthly cost under $600. At 100 daily requests, a mid-size BD2C feature like Kakao's AI writing assistant, you need horizontal scaling. 2 to 4 A100 instances with continuous batching, auto-scaling on queue depth, brings you to roughly $3,000 to $5,000 per month. At 1 million daily requests, Naver scale, full production traffic, you're looking at a dedicated GPU cluster, tensor parallelism across multiple GPUs for large models, and you need spot instance strategies and request prioritization to keep costs under $40,000 per month instead of $120,000. The auto-scaling trigger is not CPU, it is queue depth and time to first token P95 latency. When your P95 TFTFT crosses your threshold, you scale out. This is the operational metric interviewers want to hear. If you say scale on CPU utilization for an LLM system, you've already lost the round. Let's talk about how to actually win the interview question. Because knowing the architecture and communicating it under pressure are 2 completely different skills. I've watched senior engineers with 8 years of experience stumble on LLM serving questions. Not because they didn't know the content, because they answered in the wrong order. Here's the 4-step framework that consistently scores well with big tech interviewers. Step 1. State the bottleneck first. Don't start with your solution. Start with what breaks. At Sunokai daily requests, the bottleneck is GPU memory fragmentation causing low concurrency. This signals that you think in failure modes, not features. Step 2. Name the optimization. We apply paged attention via VLLM to eliminate memory fragmentation. Be specific. Name the technique. Vague answers like optimize the inference layer are invisible to interviewers. Step 3. Quantify the improvement. This increases concurrent sequences by 2 to 4x, reducing the GPU count needed from 8 to 3 for our target throughput. Demonstrate that you've operated this in the real world, not just read about it. Step 4. Name the new trade-off introduced. This is the move that separates senior from principal. The trade-off is that continuous batching's tail latency variance. P99 can spike when a long request occupies slots. We mitigate this with request length bucketing. Every optimization creates a new problem. If you can name it before the interviewer asks, you've demonstrated principal-level thinking. Practice this 4-step loop until it's automatic. Applies to every LLM infrastructure question you will face. Let's consolidate what we've covered in this chapter, because in an interview you may need to recall both patterns under time pressure. Pattern 1. The LLM gateway. Use it the moment you have multiple teams, multiple models, or need cost visibility. It adds 5 to 15 milliseconds overhead, irrelevant against LLM latency, but it gives you centralized control, fallback routing, and rate limiting. Make it stateless, put rate limit state in Redis, run multiple instances across AZs. Pattern 2. Inference optimization. The 3 pillars are KV, cache reuse, continuous batching, and quantization. The implementation vehicle is VLLM with paged attention. The cost model scales from 1 AA10G for internal tools to a full tensor parallel GPU cluster at Naver scale. Your auto-scale trigger is P95 TTFT latency, not CPU. The decision map is simple. If you control your LLM serving infrastructure, always apply inference optimization, no exceptions. If you're calling external APIs like OpenAI, the gateway is your primary lever. If you're at scale, both internal and external models, you need both simultaneously. Now here's what's coming in Chapter 3 that you absolutely cannot skip. We've covered how to serve an LLM efficiently. But a raw LLM doesn't know your company's data. That gap is where RAG architecture comes in, and naive RAG, the version 90% of candidates describe, fails in production in ways that are completely predictable and completely avoidable. We're going to show you exactly how production RAG differs from demo RAG, and why it matters for every AI system design interview you'll face. Let me be blunt. Most RAG implementations I've reviewed in technical interviews are broken by design, and the candidate doesn't even know it. The naive RAG pipeline looks simple: ingest documents, chunk them, embed each chunk, store in a vector database. Then, at query time, embed the question, do a cosine similarity search, grab the top K chunks, and inject them into the LLM prompt. Clean, elegant, and dangerously naive. Here are the 3 failure points nobody talks about in interviews. First, fixed-size chunking at FOV12 tokens blindly splits mid-sentence, destroying semantic coherence. Your embedding literally doesn't know what the chunk means. Second, using a single generic embedding model like text embedding ADA002 for domain-specific Korean financial documents produces garbage retrieval quality. The embedding space doesn't align with your vocabulary. Third, top K retrieval with no re-ranking means you're injecting contextually irrelevant chunks into your prompt, and the LLM confidently hallucinates using that garbage context. I've seen this exact pattern cause a production chatbot at a major Korean insurance company give wrong policy details to real customers. But here's the thing. Fixing these 3 points alone gets you 60% of the way to production quality. The next scene will show you exactly how advanced RAG addresses each one. Now let's talk about what separates a junior RAG design from a senior one in an interview. Advanced RAG introduces 3 surgical upgrades. First is high-day, hypothetical document embeddings. Instead of embedding the raw user query, you ask the LLM to generate a hypothetical answer first, then embed that. Why does this work? Because a hypothetical answer lives in the same vector space as real documents. A question like what is Hyperclova's context window sits in a different embedding neighborhood than the actual document that answered. Heidi closes that gap. The trade-off. One extra LLM call adds 200 to 400 milliseconds latency. Second is hybrid search, combining BMTN25 sparse retrieval with dense vector retrieval using a reciprocal rank fusion score. BM25 is unbeatable for exact keyword matches, product codes, person names, Korean legal terminology. Dense retrieval wins on semantic similarity. In production at Naver scale, you need both. Third is cross-encoder re-ranking. After your vector search returns top 20 candidates, a cross-encoder like Cohere re-rank or a fine-tuned BERT model rescores all 20 pairs and returns the true top 3. The precision gain is dramatic, typically 15 to 25% improvement in answer. Wait, does this mean you should always use advanced RAG? The answer might surprise you in the next scene. Chunking strategy is where I've seen the most expensive mistakes. Engineers spend weeks tuning embedding models and re-rankers, while completely ignoring their 1024 token fixed chunks are the root cause of poor recall. Let me give you the framework. Fixed size chunking is fast and simple, great for prototyping, terrible for production. You'll get mid-sentence cuts that produce meaningless embeddings. Sentence boundary chunking is better. At least your chunks are semantically complete units, but sentence length variance creates uneven embedding density. Semantic chunking uses embedding similarity to detect topic shifts and cuts there. This is the current best practice for knowledge-based RAG. The downside is indexing cost, roughly 3 times slower to build. Recursive chunking, used heavily in LangChain, is a pragmatic middle ground. It tries paragraph breaks first, then sentence breaks, then character breaks, giving you natural language boundaries without the full cost of semantic analysis. For chunk size, smaller chunks like 128 to 256 tokens give higher precision but lower recall. You might retrieve the exact sentence but miss the surrounding context the LLM needs to answer correctly. Larger chunks like 512 to 1024 tokens improve recall but inject noise. The overlap parameter, typically 10 to 20%, is your safety net for boundary cases. For Korean text specifically, morpheme-aware sentence splitting is non-negotiable because Korean sentence boundaries differ significantly from English. This table tells you exactly which strategy to choose for your use case. And the next section will show you how to store and retrieve these chunks at real production scale. Let's talk about the vector database decision. And I want to be direct because I've watched engineering teams spend 3 months evaluating Pinecone vs. Weaviate vs. Milvis when the answer was sitting right in their existing PostgreSQL cluster the whole time. Here's the landscape organized by the operational maturity level that actually matters in Korean enterprise contexts. At the top, you have managed cloud services, Pinecone and Zilla's Cloud. Zero ops overhead, you're up in 30 minutes, and you pay a significant per-query premium. Good for proof of concept and startups who can't afford an infrastructure team. But here's the reality. At Naver or Kakao scale, pushing 50 million queries a day, the cost is completely prohibitive. Middle tier is self-hosted open source, Weaviate and Milvus. Milvus in particular is production battle tested at Alibaba scale and has excellent Korean community support. The operational cost is real. You need a dedicated infrastructure team. But at 10 million DAU, you own the cost curve. Bottom tier is pvector, the PostgreSQL extension, if your data is already in PostgreSQL. And for most Korean enterprise applications, it is pvector with HNSW index handles up to about 5 million vectors with excellent query performance. The integration cost is near zero. The decision framework for interviews is simple. Under 1 meta vectors and no dedicated infra team, use pgvector. To 50 million vectors with team capacity, use Milvus or Weaviate self-hosted. Over 50 million vectors with complex filtering needs, you're building a custom solution anyway. But choosing the right store is only half the problem. The index type will make or break your P99 latency. This is the scene I want every architect to internalize before their system design interview. Because HNSW versus IVF is one of the most asked and most incorrectly answered questions I've encountered. Let me give you the intuition first. HNSW, hierarchical navigable small world, builds a multi-layer graph where each vector is connected to its nearest neighbors. Search traverses from the top sparse layer down to the dense bottom layer. It's like navigating a city. You take highways first, then local roads. The result is exceptional recall, typically 95 to 99%, with query latency in the 1 to 10 millisecond range. The cost. Build time is LLM and memory consumption is significant. Roughly 100 bytes per vector for a 128-dimensional floaty32 embedding. At 100 million vectors, that's 10 gigabytes just for the index graph. IVF, inverted file index, clusters your vector space into Voronoi cells using k-means. Then at query time searches only the nearest n clusters. Memory efficient and fast to build. But here's the critical failure mode. If your query vector lands near a cluster boundary, you miss its nearest neighbors entirely because they're in an adjacent cluster you didn't search. At 100 million vectors with default and probe settings, I've measured P99 retrieval latency, 500 milliseconds, and recall dropping below 80%. The interview answer is, use HNSW for latency-sensitive production RAG where recall matters. Use IVF with flat only when memory is the hard constraint, and you can accept the recall trade-off. And whatever you do, never use IVF flat without tuning nprobe. The default values and face are optimized for benchmarks, not for your data distribution. Metadata filtering is where naive RAG implementations quietly die in production, and most candidates have never thought about it until the interviewer asks. Here's the scenario. You have a document corpus containing financial reports from 2019 through 2024 across multiple companies. The user asks what was Samsung's revenue in 2023. Without metadata filtering, your vector search returns semantically similar chunks from the wrong year and wrong company. Garbage in, hallucination out. There are two approaches. Pre-filter applies metadata conditions for the vector search. You first narrow the candidate set to documents matching company, Samsung and Edir, then run AN search only within that subset. This is precise but has a critical failure mode. If the filtered subset is too small, say fewer than a few hundred vectors, HNSW graph connectivity degrades and recall collapses. You need a minimum viable candidate pool size. Post-filter runs the vector search first across the full index, then applies metadata filtering to the results. The problem here is obvious. If your top 100 results contain only 3 documents matching your filter criteria, your effective top K becomes 3, not 10. For production hybrid search architecture, the answer is a 2-stage pipeline. Sparse BM25 retrieval and dense vector retrieval run in parallel, each with their own metadata pre-filters, and the results are merged using reciprocal rank fusion before hitting the re-ranker. This is the architecture Elasticsearch's native vector search and Weaviate's hybrid search implement under the hood. The next scene connects this to the actual scale constraints of Korean services. Let me ground everything we've covered in the actual reality of Korean services at scale. Because this is the context that separates a textbook answer from a senior architect answer in any interview. Naver's hyperclova-based search and recommendation systems operate on index sizes in the hundreds of millions of vectors. Their ARS AI recommendation system has been processing tens of millions of daily active users since 2021. The critical architectural constraint isn't retrieval quality. It's index update latency. Naver's content index needs to reflect new articles published minutes ago. That means they cannot afford HNSW index rebuilds. They use a segmented index architecture where new content lands in a small, fresh segment with brute force search, and the bulk of the corpus uses HNSW. Periodic segment merges happen during off-peak hours. Kakao's AI platform faces a different constraint. Multi-language retrieval across Korean, Japanese, and English content for the same semantic query. Their embedding model needs to be a multilingual model. They can't use separate models per language, because that would require separate indexes and query routing logic. The architecture lesson here is that the optimal RAG design is completely determined by your update frequency, language requirements, and scale, not by what the latest LangChain tutorial recommends. When an interviewer asks how would you design RAG for a Korean news platform with 10 million DAU, this is the framework you anchor your answer to. Now let's talk about how you prove your RAG system actually works before shipping it. Alright, before you ship any RAG system to production, run through this checklist. I'm not joking when I say I've done postmortems on RAG systems that failed all 5 of these checks simultaneously. First, chunking validation. Don't assume your chunking is working. Actually inspect 100 random chunks and verify semantic coherence. Run a retrieval smoke test. Take 20 known question-answer pairs from your corpus and verify the correct chunk appears in top 5 results. If it doesn't, your chunking is broken. Second, embedding model benchmarking. For Korean domain-specific content, benchmark at least 3 embedding models: OpenAI text embedding 3 large, multilingual E5 large, and a Korean-specific model like Kosim Sesi Roberta. Don't just use whatever LangChain defaults to. Measure NDCG on your actual data. RAGAS evaluation. This is non-negotiable for production. RAGAS gives you 4 critical metrics. Faithfulness measures whether the generated answer is grounded in the retrieved context. This is your hallucination detector. Answer relevance measures whether the answer actually addresses the question. Context recall measures whether the relevant documents were retrieved at all. Context precision measures whether the retrieved documents were actually relevant. Ultimate RAGAS scoring in your CI/CD pipeline. Any regression above 5% in faithfulness should block deployment. Fourth, re-ranker integration testing. Measure the precision lift from your re-ranker on your specific domain. If it's less than 5% improvement, the added latency isn't worth it. Fifth, define your latency SLA before you optimize. I've seen teams spend weeks shaving 20 milliseconds off a pipeline with a 2-second SLA. Know your numbers. Typical production RAG targets are P50 under 399 and under 800 milliseconds for interactive use cases. This checklist is what separates systems that survive production from demos that look good in a slide deck. Let me close this chapter with the decision framework that ties everything together. The RAG architecture decision tree. You're in a system design interview. The interviewer says design a RAG system for our internal knowledge base. Here's how you answer without falling into the 90% trap. First question. What is the corpus size and update frequency? Under 100K documents with weekly batch updates, naive RAG with peak vector and recursive chunking is completely sufficient. Over-engineering this is a red flag. Second question. What are the retrieval quality requirements? If the use case is customer-facing and wrong answers have business consequences, insurance claims, legal documents, financial advice, you must have hybrid search plus or ranking. The faithfulness score needs to be above 85%. Third question. What is the query latency SLA? Under 500 millisecond P99 for interactive. HNSW is mandatory, and you need to profile your re-ranker latency carefully. Over 2 seconds acceptable, you have more flexibility. Fourth question. Is this agentic? Can the system issue multiple retrieval calls, reformulate queries, or use tools? If yes, and this is where the next chapter begins, you've outgrown RAG and you're designing an agent orchestration system. The jump from RAG agents is not incremental. It's a completely different architecture with completely different failure modes. In the next chapter, we're going to tear apart agent orchestration patterns, React loops, tool use, multi-agent coordination, and the orchestration layer that holds it all together. If RAG is the foundation, agents are the superstructure, and getting the interface between them wrong is where most AI systems fail at scale. All right, let's talk about agents, because this is where most interview candidates completely fall apart. They say I'd use an LLM agent and then go blank when the interviewer asks, okay, but how does it actually work? So let's nail this. The React pattern, reasoning and acting, is the foundational loop. The LLM receives a question, reasons about tool to call, emits an action, the runtime executes, feeds back the observation, and the LLM reasons again. This repeats until the LLM decides to emit a final answer. Sounds clean, right? Here's where it breaks in production. First, infinite loops. The LLM gets confused mid-chain and keeps calling the same tool. You need a hard actions cap. I set mine to 10 in LangChain. Second, tool call failures. If your search API returns a 5-3, your agent just halts. You need retry logic with exponential backoff wrapped around every tool. Third, and this kills me every time, The LLM reasons correctly, but formats the action output wrong, so the tool parser throws an exception. Always validate tool call JSON before execution. Naver's ARS recommendation agents hit this exact wall in early 2023. The fix? A structured output parser with fallback to a repair prompt. But wait, React's biggest flaw isn't tool failures. It's something far more expensive. And I'll show you in the next scene. Here's the expensive truth about React. It's inherently sequential. Every tool call adds one full LLM round trip of latency. If your task needs 5 tool calls, that's 5x the latency stacked in series. For a customer-facing chatbot, that's the difference between a 2-second response and a 10-second timeout. This is exactly why Plan and Execute was introduced. The architecture splits into 2 phases. A planner LLM takes the user query, decomposes it into a full task graph upfront. Think of it like a compiler generating an execution plan. Then an executor runs those tasks, and critically, independent subtasks can run in parallel. Let me make this concrete. Imagine a multi-step analytics query: fetch sales data, fetch competitor prices, fetch weather data, then synthesize. In React, that's 4 sequential LLM calls. In Plan and Execute with parallel execution, the first 3 runs simultaneously, your wall clock latency drops by 60%. LangGraph natively supports this with parallel node execution. AutoGen takes it further with conversational agent coordination. But here's the trade-off you must state in interview. Plan and Execute has a higher upfront planning cost, and if the plan is wrong, which happens about 50% of the time in my experience, replanning is expensive. React is more adaptive but slower. The winning answer in interviews? Use React for short, unpredictable tasks. Use Plan and Execute for long, structured workflows with known subtask shapes. What happens when one agent simply isn't enough? When a single agent can't handle the complexity, whether due to context window limits, specialization needs, or fault isolation requirements, you go multi-agent. The canonical topology is orchestrator worker. The orchestrator agent owns the user-facing conversation state and the task plan. It dispatches subtasks to specialized worker agents, a SQL agent, a web search agent, a code execution agent, each operating independently. Communication between them happens over a message bus. In production, you'd use Redis streams or Kafka, not direct function calls. Why? Because async messaging gives you retrace semantics, backpressure, and dead letter queues when a worker crashes. This is the part that nobody teaches. Task state management across agent boundaries. Each agent is stateless in itself. All state lives in a shared state store, typically Redis for hot state and PostgreSQL for durable state. The orchestrator writes a task manifest with status fields: pending, in progress, doing, failed. Workers claim tasks optimistically and update status atomically. This is basically a distributed task queue pattern. And if you've designed microservices before, this should feel familiar. The critical interview answer here is, agents are not magic. They're distributed systems with all the same failure modes: network partitions, duplicate execution, partial failures. Design them accordingly. Line's customer service AI uses exactly this topology, with 6 specialized worker agents behind a single orchestrator. Coming up next, we need to talk about the one thing that makes agents truly stateful, and why most teams get it completely wrong. Here's a question that trips up almost every candidate. How does your agent remember things? Most people say conversation history in the prompt and stop there. That's only one of 4 memory types, and it's the most limited one. Let me map this out properly. First, in-context memory. This is your raw conversation history stuffed into the system prompt. Capacity is hard limited by your context window. GPT-4 gives you 128k tokens, but at fang per 1k input tokens. A 100k token context costs per call. At scale, that's brutal. Second, external short-term memory. Session scope state stored in Redis, with a TTL. Fast retrieval, cheap, and survives LLM restarts. This is we put the last 10 turns of conversation after compressing older turns. Third, long-term episodic memory. User-specific interaction history stored in a vector database. Things like this user always prefers concise answers, or last Tuesday, they asked about X retrieved via semantic search at session start. Fourth, semantic knowledge memory. Your RAG knowledge base, the domains the agent can look up. This is the external long-term memory for facts, not user-specific history. The backend mapping matters for your interview. In-context uses LLM's own KV cache. Short-term uses Redis. Episodic uses Pinecone or Weaviate with user-scoped namespaces. Semantic uses Yoragi vector store. Each tier has different latency, cost, and capacity trade-offs. But knowing the 4 types is table stakes. The real production challenge is how you manage the transition between them. And that's a pipeline that most teams build wrong. Now let me show you the production memory management pipeline, because this is where teams actually ship broken systems. Imagine a customer service session that's been running for 200 turns. You cannot fit all 200 turns into a 128K context window affordably. Here's the pipeline we actually run. Step 1. Conversation buffering. Every new turn is appended to a rolling buffer in Redis. We keep the raw last 20 turns verbatim. These are your hot, recent context. Step 2. Sliding window truncation. When the buffer exceeds 20 turns, we drop the oldest turns from the in-context prompt, but we don't throw them away. Step 3. LLM-based summarization. Every time we evict a batch of 10 turns, we run a cheap fast model, GPT-4 Mini or Claude Haiku, to summarize those turns into 2 to 3 sentences. This summary gets prepended to the system prompt as conversation background. Cost, about $0.01 per summarization. Savings, eliminating 10 turns worth of tokens from every future call. Step 4. Persistent storage. The raw turns go to PostgreSQL for audit and compliance. The summary and semantic embeddings of key facts go to Pinecone under the user's ID. At the next session, we bootstrap by fetching the last summary plus semantic memories. This pipeline reduced our per-session token cost by 73% in a product chatbot handling 50K daily active users. The anti-pattern I see constantly, teams just trunk it from the left. No summarization, no persistence. Users feel like the bot has amnesia every 20 messages. That's a retention killer. Now, you've built an agent that remembers. But how do you make sure it doesn't something catastrophically wrong? Let me tell you about a real incident. A Korean fintech company launched an LLM chatbot in 2023. 3 days in, a user crafted a prompt that made the bot reveal internal system prompt instructions, a classic prompt injection. The bot was taken down for 48 hours. Regulatory inquiry followed. This is why guardrails are not optional, they are your production readiness gate. The guardrail stack has 4 layers, and you must be able to name all 4 in an interview. Layer 1, the outermost, input sanitization. Strip PO before it hits the LLM. Korean RRM patterns, credit card numbers, phone numbers. Run a prompt injection classifier. We use a fine-tuned DeBerta model that adds only 15 milliseconds latency. Reject or rewrite hostile inputs before they touch your expensive LLM call. Layer 2. Prompt construction safety. Your system prompt must include explicit role binding instructions. Never cat your input directly into tool call arguments. Always parameterize. Layer 3. Output safety classification. After the LLM generates a response, run it through a safety classifier. NSFW, toxicity, leakage detection. OpenAI's moderation API is free and covers the basics. For domain-specific safety, you need a custom classifier. Layer 4, the innermost, factuality verification. For high-stakes domains, medical, legal, financial, run an NLI-based fact-checker against your retrieved documents. Flag responses where the claim is not entailed by any retrieved chunk. This is your hallucination detection layer. The total overhead, 30 to 50 milliseconds for layers 1 to 3, 100 to 200 milliseconds for layer 4. Budget it into your latency SLO. But guardrails without observability are flying blind, and that's what we cover next. Final pattern of this chapter, and arguably the one that separates amateur AI projects from production-grade systems. Observability. Without it, you are completely blind. You cannot debug why a user got a bad answer. You cannot know if your hallucination rate is 2% or 3%. You cannot optimize costs because you don't know which agent step is burning tokens. Here's the AI observability pipeline run. Step 1. Distributed tracing. Every agent invocation gets a trace ID. Every step. LLM call, tool execution, retrieval query is a span. Use LangSmith for LangChain-based systems or Helicon as a proxy for any OpenAI-compatible endpoint. You get a full waterfall view. Which step took 800 milliseconds, which tool call failed, what the exact prompt was. This is priceless for debugging. Step 2. Token cost attribution. Tag every LLM call with metadata, user ID, session ID, feature name, agent step name. Then aggregate in your data warehouse. You will find that 10% of users drive 60% of token costs. That 10% probably contains your power users and your prompt injection attackers. Step 3. Retrieval quality logging. Log the top K retrieved chunks and their similarity scores for every RAG query. Then compute MRR and NDCG offline. If retrieval quality degrades, maybe your vector indexed, after a data update, your answer quality tanks silent without this. Step 4. SLO alerting. Define hallucination rate as a service level objective. We target less than 3% of hallucination rate measured by our factuality classifier. Alert when P95 latency exceeds 3 seconds or hallucination rate exceeds threshold. PagerDuty integration, same as your backend services. The point I want you to take into your next interview. AI systems are distributed systems. Apply every observability principle, already know, traces, mecs, logs, alerting, and extend them for AI-specific signals. In the next chapter, we're going to talk about what actually breaks at real scale. The war stories from systems handling millions of LLM calls per day that no textbook will ever tell you. Let me tell you about a real incident that happened during a major Korean portal shopping season. Think of it as their Black Friday equivalent. A RAG-based customer service chatbot was handling return and refund queries. Everything looked fine in staging. Load tests passed. The team shipped with confidence. Then traffic hit 40x normal volume at 10 p.m. With 8 minutes, P99 latency went from 800 milliseconds to 47 seconds. Users were getting timeout errors. The on-call engineer was paged. Here is what the postmortem revealed. The embedding model, a single GPU instance running sentence transformers, became the single point of failure. Every incoming query needed to be embedded before vector search could even begin. The embedding service queue backed up to 12,000 requests. The vector DB itself, Pinecone in this case, was completely healthy. The LLM inference layer was completely healthy. Because nobody had horizontally scaled the embedding throughput, the entire pipeline collapsed at the very first step. The cache hit rate was only 11%. Because customer queries during a sale event are naturally diverse, "Can I return this jacket I bought 3 hours ago?" is not a query you cached. This is what I call the embedding bottleneck trap. You spend weeks optimizing your LLM inference, you add KV caching, using your prompt, and then 8 cell per hour embedding model takes down your entire system. But here is where the story gets more interesting. The fix they applied in production was not what you would expect from a textbook. Now let me show you a failure mode that's even more dangerous because it burns silently before anyone notices. This is the agent infinite loop scenario, and I have seen this happen at 2 separate Korean AI startups within the same quarter. The setup: a customer support agent is given tools, a CRM lookup tool, an order status API, and a refund initiation tool. A user asks, "Where is my order?" The agent calls the order status API. The API returns a response like, "Order 9234, status. In transit, verification." The agent does not know what pending verification means. It is an ambiguous state. So the agent does the reasonable thing. It calls the tool again, same ambiguous response. It tries to call the CRM tool to get more context. CRM returns a partial record. The agent decides it needs more information and loops back. Within 3 hours, this single session has made 147 tool calls, 2.3 million tokens, and cost $100 for one customer query. Multiply that by concurrent sessions, and you have a Wisconsin surprise on your cloud bill by morning. The 3 circuit breaker patterns that prevent this are: hard iteration caps never allow more than 10 tool calls per agent session, period. Second, tool call deduplication. If the same tool is called with the same arguments within the same session, short circuit immediately with a cached result. Third, ambiguity detection. If an LLM response contains hedging phrases like "I need more information" for more than 3 consecutive turns, escalate to human handoff instead of retrying. These 3 patterns cost you maybe 2 implement. Not having them costs you your job. And here is the uncomfortable truth about the next topic. Some of the architectures that score highest in interviews are the ones most likely to produce exactly this kind of failure in production. Here is the uncomfortable part of this chapter. I have reviewed hundreds of system design interview transcripts, and I keep seeing the same 3 architectures that interviewers nod along to, and that I have personally watched fail in production within 6 months of launch. Anti-pattern number 1. Using a fully managed vector database like Pinecone or Weaviate Cloud for a corpus of 10,000 documents. In an interview, this sounds sophisticated. In production, you are paying $30 per month for infrastructure that a face index loaded into application memory would handle in 50 milliseconds with 0 network hops and 0 cost. The managed vector DB makes sense at 10 million documents. At 10,000, it is pure over-engineering. Anti-pattern number 2. Designing a multi-agent system when a single agent with 4 tools would solve the problem. Candidates draw beautiful orchestrator worker diagrams with 5 specialized agents. Interviewers love the sophistication, but every agent boundary is a serialization point, a latency addition, and a new failure mode. If your agents communicate over HTTP, you have just introduced distributed systems failure modes into could have been a simple function call chain. Anti-pattern number 3. Skipping the re-ranker to save 50 milliseconds of latency. Teams skip re-ranking because it adds latency. But without re-ranking, your RAG system retrieves the top 5 chunks by cosine similarity, which is a proxy metric, not a relevance metric. Users get confidently wrong answers. The 50 milliseconds you saves you user trust. Now here is the pattern that connects all 3 of these. They are all examples of optimizing the wrong variable. And the checklist I am about to show you will prevent exactly this mistake. So after 25 years of building systems and watching them break, here is the single most important principle I can give you. Complexity must be earned, not assumed. The teams that the most reliable AI systems I have seen, at Naver, at Kakao, at Line, they all follow the same progression. They start with the dumbest thing that could possibly work. They measure it ruthlessly, and they add complexity only when the measurements prove it is necessary. Here is the incremental complexity checklist I now use in every architecture review. Step 1. Validate naive RAG first. Chunking plus embedding plus cosine search plus generation. No re-ranker, no agents, no fancy query rewriting. Gets working and measure your baseline precision. Step 2. Measure recall. If recall at 5 is above 0.75, your retrieval is good enough. If it is below that, add a cross-encoder re-ranker, not before you measure. Add query rewriting only if you observe users asking multi-part or ambiguous questions in your actual query logs. Step 4. Add agents only when you have a specific tool use case that a single LLM call cannot handle, like needing to call a live API or execute code. Step 5. Add multi-agent orchestration only when you have proven that a single agent is a bottleneck due to context length or parallelism requirements. Every layer you add without this evidence is technical debt you will pay during an incident at 2 a.m. In the next chapter, we are going to take everything from this entire lecture and turn it into a concrete interview framework. The exact structure you use to answer any AI system design question in 35 minutes, and make the interviewer feel they just spoke to someone who has actually shipped these systems, because now you have. Here's the brutal truth. Most candidates fail AI system design interviews, not because they lack knowledge, but because they freeze at the blank whiteboard. They know LLM serving, they know RAG, they know vector databases. But when the interviewer says design an AI-powered customer support system, their brain blanks out. So here's the master weapon, a 7-pattern decision tree you can execute in under 60 seconds for any prompt. Step 1. Is the system doing inference or retrieval? If pure inference, you're in LLM serving territory. Think KV cache, batching, GPU scheduling. If retrieval is involved, branch to RAG. Step 2. Is the RAG single hop or multi-hop? Single hop goes to naive RAG with HNSW index and embedding cache. Multi-hop spawns an agentic RAG branch with tool calling loops and memory. Step 3. Is there a feedback loop? If yes, you're in RLHF or online learning territory. Step 4. Is latency under 200 milliseconds a hard constraint? That forces streaming inference, speculative decoding, and edge caching. Step 5. Is the data peer sensitive? Korea's PIPA and GDPR branch kicks in. On vector store, audit logging, data residency. Step 6. Is cost the primary constraint? That pushes you to quantization, spot GPU fleets, and model distillation. Step 7. Is it a multimodal system? Vision language models, cross-modal retrieval, separate, embedding pipelines. Nail these 7 branches in 60 seconds, and you've already scored higher than 80% of candidates. But there's one branching mistake that almost everyone makes at step 3. I'll show you exactly what it is right now. Now let's talk about how interviewers actually score you, because this is where the real gap between senior and junior candidates shows. At companies like Naver, Kakao, and Line, the system design panel typically scores on 4 dimensions. First, architecture correctness, worth 30%. Did you pick the right components? Did you avoid obvious mismatches like using a relational database as a vector store? Second, trade-off awareness. This is actually worth 35%, the highest weight. Can you articulate why you chose VLLM over TGI? Can you explain the memory throughput trade-off of paged attention? This is what separates staff engineers from senior engineers. Third, scalability reasoning, 20%. Can you explain what breaks first when traffic goes 10 amps? Can you identify the bottleneck? Is it the embedding service, the re-ranker, or the LLM itself? Fourth, production readiness, 15%. Did you mention observability? Did you account for model drift, cold start, and graceful degradation? Here's the counterintuitive insight. Most candidates overinvest in architecture correctness and say almost nothing about trade-offs. But interviewers at senior levels weight trade-off awareness the most, because in real production, you're always choosing between 2 imperfect options. The candidate who says I chose this because of X and the cost is Y, which I mitigate with Z wins every time. This scoring framework is your unfair advantage. Use it to self-audit your answer in real time during the interview. Let me give you the exact do-don't list that I've distilled from hundreds of system design interviews. And from being on the interviewer side myself. 5 things you must always say. 1. Always state your scale assumptions up front. I'm assuming 10 million DIU, 50 QPS at peak, P99 latency target of 500 milliseconds. This immediately signals engineering maturity. 2. Always name the failure mode before proposing the solution. The naive approach fails because vector index becomes stale, so I add an incremental update pipeline. 3. Always quantify your trade-offs. Not just it's faster, Say speculative decoding reduces TFT by 40% at a 15% memory overhead cost. 4. Always mention the Korean regulatory context if relevant, PIPA data residency, on-prem vector store, audit logging. This differentiates you from candidates who studied only US-centric resources. 5. Always close with an operational concern. In production, I'd add Prometheus metrics on queue depth and can throughput, with a PagerDuty alert at 80% GPU utilization. Now the 5 instant junior signals. 1. Saying just use ChatGPT API without discussing cost, latency, or data privacy. 2. Designing a system with no fallback. What happens when the LLMs is down? 3. Ignoring chunking strategy in RAG. Chunk size is not a detail, it's the most impactful hyperparameter. 4. Proposing a monolithic embedding service that does retrieval, re-ranking, and generation all in one process. 5. Never mentioning cost. GPU hours are expensive, and not having a cost model is a red flag at any senior level. The gap between a higher and a strong higher verdict is almost always in these 5 points. Coming up next, the exact 4-week plan to internalize all of this so it flows naturally under interview pressure. We've covered every layer, from LLM serving internals and RAG architecture to agent loops, real-scale failure stories, and the interview scoring framework. Now the only question is, what do you do with all of this in the next 4 weeks? Here's the concrete roadmap. Week 1. LLM serving mastery. Deploy VLLM locally, benchmark throughput versus latency trade-offs with different batch sizes, and implement a streaming endpoint. Read the page detention paper, not to memorize equations, but to explain the KV cache fragmentation problem in your own words. Week 2. RAG architecture. Build a full RAG pipeline from scratch, embedding HNSW index, retrieval, re-ranking with a cross-encoder, and generation. Deliberately break it, use bad chunk sizes, skip re-ranking, and measure the quality drop. You learn RAG by breaking RAG. Week 3. And multi-step systems. Implement a simple React agent with tool calling. Add observability, trace every tool call, measure latency per hop, and simulate a tool failure to see how the loop degrades. Week 4. Mock interviews only. Take everything you built and practice explaining it out loud. To a mirror, to a colleague, to an AI. Time yourself. You must be able to draw the full architecture and articulate all trade-offs in 20 minutes. The 3 most effective practice sources. First, the BLLM GitHub issues, real production bugs, real trade-off discussion. Second, Naver Tech Blog and Kakao Tech Blog, Korean scale AI infra stories that ByteByteGo doesn't cover. Third, this lecture series, rewatch each chapter and try to answer the interview question cold before I explain it. This is the end of the series, but it's the beginning of your preparation. Every senior engineer you admire built their intuition by going through exactly this cycle: build, break, explain, repeat. Now it's your turn. Go build something that breaks at scale, and then you'll know how to design something that doesn't.